Second, yeah. I'm just sharing my screen, and in this live video, we are going to attend this workshop for reinforcement learning and how modern LLMs are trained. Yeah, LLMs are quite new, so attaching modern in front of it seems quite, yeah, weird, but like some paradigm shift is there, so that's why I'm calling it modern. Okay, start.
The open source models and closed source models in terms of MLU, they've kind of like reached the same accuracy, right? So like you can see that, okay, this is already outdated, but in general, you see like Llama 3.1, 405 billion kind of reached, GPT-4o level. So open source models definitely have caught up to closed source models. However, there is a however. Recent, like since September 2024, I would call this something called the open source drought. No one wants to talk about it, but I will. Right, so like September 2024, O1 got released, O1 preview. And to be honest, the open source community was shocked. Right, so like suddenly the capabilities diverged. Right, so there's something called the MLU plateau where most models, the open source models and the closed source models, they kind of converged. So the open source models was equivalent to the closed source models. But suddenly in 2024 September, OpenAI released O1 preview, and it kind of shocked the entire community because the capability or intelligence kind of skyrocketed, right? So like with reasoning, long reasoning traces, it just was a total change of mindset. And for 4 months, the open source community kind of died internally because there was nothing, we can't replicate it. We don't know what to do. Do we do this? Do we do that? I don't know. But then suddenly in 2025 January, DeepSeek R1 came along and they released R1. And that's when the entire world kind of changed their view, right? So like you can in fact train open source models to be as powerful as O1 or O3 or whatever, right? So like that was what I call the open source drought. However, there was a previous drought even before that. Remember when ChatGPT got released in 2022 December, right? So like before even ChatGPT, most models were base models. They were not really instruct fine-tuned that well. And so most large pre-trained models were actually useless, but they were terrible. But then suddenly ChatGPT came along and they did better, reinforcement learning from human feedback, better instruction fine-tuning, better instruction following, and it really changed the world, right? So like, I think large language models were already here before 2022, right? They were already there. But it was just ChatGPT which showed that if you have good data, right, good instructions, good answers, good supervised fine-tuning, and good reinforcement learning, you can actually make the model very useful. And yes, again, open source had a delay, a very long delay, right, until like Llama 1, I guess. And so always, I would say open source always tries to catch up to the closed source models. The next question is, what is after reasoning? Is there going to be something else? I think that's a very good question. My personal take is it's going to be very hard. I think reasoning was like the DeepSeek R1 paper said that most likely the model already has these reasoning capabilities, and we just need to accentuate them. And so like, I'm not sure if there's going to be some other new, like step function where we'll get to like the next capability. But in my view, I think like every single time the closed source models will always do like a step function. But who knows? Maybe now it will plateau forever. I don't know. So that's like, you have like long discussions about, if AGI is going to come or not, like, but who knows? The talk is not going to be about that, but yes. Next. So I call the first jump the SFT or RLHF jump, right? So like that's essentially if you do good supervised.
It aims to improve LM models by which is a form of providing human feedback. This feedback is crucial as it helps train the RLHF reward model, which in turn guides the LLM to produce better outputs. In essence, by selecting preferred responses, you help the LLM learn what is more aligned with human expectations. So what are the steps in training an LLM with RLHF? Well, first you start with foundation allows you to focus on the model to align with specific human values and preferences. Some of the creative models they just like resources are really all existing knowledge. Yeah, but that's what they get human feedback. So how is human feedback collected? Human feedback is gathered by evaluating LLM outputs, often in preference comparison and regulatory potential. This feedback is used to train a reward model, which
It simply means that if you want to do research, maybe you can take a pre-trained model and do your research on top of it, because it may be cheaper and more fast, and there could be lot many things that you can try, and uh, maybe you can think pre-training is like you're given a newborn baby, and you can you can have a certain way of teaching it that is better than all those best of labs, like all those research labs or AI labs. Maybe you have some way that you can teach that newborn baby better than those. So if you want to do research, taking a pre-trained model and working your way up would be a better thing to do. So pre-training and training process, what we do is we tokenize the internet text into sequences. We mask next token. We try to predict it. We calculate loss, update weights. We repeat for trillions of tokens. Weight changes from random to meaningful. So it's just next token prediction. You mask the next token. You ask the model to predict the next token. It predicts. Then you see what was, maybe you have some kind of loss, maybe cross entropy or some other thing or whatever, and you have some optimization function as well. You have some learning rates for all those weights, and you follow, yeah, you follow this process for quite some time, and you have pre-trained your model. During, what it does is it teaches model to follow instructions, learn question answer patterns, adapts to a conversational format. So in supervised fine tuning, it's like you you make it responds make it respond to a chat conversation. You tell it that this is the human and you are the AI, and if human is asking something, then you are supposed to answer it with thoughtful and mindful ways. So I think at the supervised fine tuning stage, they are introducing maybe tokens like, yeah, this is the human user, and he said that, and human conversation ended, AI conversation started, and now you have to tell something. And at this particular stage, it is learning to do that. So how it does is we teach model to follow instruction. We learn question answer pattern, adapt to conversational format, training process, curate instruction response pairs. You have to do that. Supervised learning on conversations, fine tune existing weights, validate on held out examples, weight changes, task adaptations on top of base knowledge. So in SFT example, maybe it's the same thing that next token prediction, but this time if you ask it to explain photosynthesis, and you tell it this is the input, and then you give it key, this is your output token, and now you're supposed to produce some output, then it will give a structured response, not just completion. And this may not align with the human preferences. Maybe if you ask it to make nuclear bomb, it will give you the exact thing. But this is like in supervised fine tuning, maybe you want model to give its best out there, and you tell it that it won't be judged, or there is no bias against it or nothing like that. And in the RLHF, yeah, what it does is it aligns the model with human preferences. So in RLHF, we have some preference for certain kind of outputs, and we train the reward model on that data. And whenever LLM produces an output, we check that as per the reward model or reward policy model, what should be the reward that should be given to LLM for producing this kind of output. And then we change the weights that it should not produce this kind of output, and maybe there can be those. So this RLHF or this reward model act as a loss function or something like that. Teaches helpful, harmless, honest behavior, optimizes for human preferred outputs, training process RLHF, collect human preferences, data A versus B, train reward model to predict preferences, use PPO to optimize against reward model, iteratively improve alignment, fine-grained preferences optimizations, strengthens helpful behavior, suppresses harmful outputs. Yeah, here. So, so RL examples are pretty interesting, I guess. How to make explosives. Previously, model would tell ki, yeah, provide dangerous instruction because uh, is not biased or it doesn't have any human opinion around it. So it is giving you the best answer possible. Now after RL, it will say, I can't help you with that. Explain quantum physics, technically correct but confusing before RL, and after RL, clear, helpful explanation which humans prefer. So the interesting thing is RL data is very less, 1 MB of preferences, human rankings, and SFT it could be just 10 MB of examples, thousand of conversations. Just tens of GPUs for days should be enough. Yeah, tens of GPUs for hours should be enough. So we can actually find some data set of RLHF and train our own uh, so, like instruct tuned models. If something is instruct tuned, we can run RL on top of it. It's quite interesting, and we should do that in the coming weeks. And it's saying that for pre-training, it is cross entropy next token prediction, but I am not sure how these two works. Cross entropy is supposed to sequence and policy gradient reward optimization. So what I want to learn is what is sequence to sequence cross entropy. So a sequence to sequence model is an encoded decoder neural network architecture that uses cross entropy laws to train the model to predict an output sequence from a given input sequence. This approach is widely used in tasks like machine translations and text summarization, where both input and outputs are sequences of potentially different lengths. Sequence to sequence model architecture. This encoder decoder framework typically uses cross entropy serves as a standard loss function for this token level classification task calculation. At each step, the decoder's predicted probability distribution is compared to the actual target token. The model minimizes the difference between predicted and actual distributions or backpropagation. What we want to learn is in supervised fine tuning. Instead of evaluating the entire generated sequence as a single unit, instead of evaluating the entire generated sequence as a single unit, the loss is calculated at each time step as the model generates an output token. The total loss for single input output pair is the sum of the individual cross entropy losses for the every token in the generated output sequence. Guiding the model. This aggregates loss value is then used by the optimization algorithm like backpropagation to adjust the model's parameter, encouraging it to produce output that match the ground to target sequence more accurately. A common technique used during training is teacher forcing. In this approach, and at each step, the model is fed the actual correct previous token. In this approach, at each step, the model is fed the actual correct previous token from the training data as input for the next prediction rather than the token predicted itself in the previous step. This accelerates the training and prevents the model from propagating its own error through the sequence. The loss computation handles sequence of different lengths. In text summarization, where the sum is shorter than the source text, by typically using padding or stopping the loss calculation at a special end of sequence token. The loss is typically calculated only on the response target portion of the data while the input from tokens are masked. So, how does cross entropy loss calculations differ in SFP and pretending? While the mathematical formula for cross entropy loss remains the same, the key difference between supervised fine tuning and pretending is which token contribute to what that loss. Loss masking. The where in pretending the loss is typically calculated over the entire sequence. Since the goal is to generate language modeling, every token except padding is a target for the next token prediction. SFT loss is typically zeroed out on the prompt instruction and calculated on the response target. This ensures the model focuses on learning how to answer rather than memorizing the user's question. uses massive unsupervised and often noisy datasets. The model learns natural grammar, facts, and reasoning. SFT uses a smaller curated dataset of high quality instruction response pair. The goal is alignment, teaching the model a specific voice or task following behavior, convergence, and learning rate. Retraining requires a higher learning rate of millions of steps to converge because it starts from random weights. Converges much faster, often in 1 to 3 epochs, because the model already knows language. The loss decreases rapidly as it adapts to specific formatting and style of the supervised data. Enter text sequence, response completion only. Can you teach me via a real example? This should be fun. So in pre-training, the model is taught to predict the next token for every single word in the text. Every token in the sequence acts as a label for the one before it. So input sequence is what is the capital of France? The capital is Paris. The model calculates the cross entropy loss for every prediction made across the entire string. The model learns general grammar facts. So model predicts every token, and then the loss is propagated. In SFT, we specifically want the model to learn the answer, not how to rewrite the question. So here it's saying that it's sequence to sequence, and this is per token, and here you first calculate the loss for the whole sentence, and then you propagate it, something like that. What is policy gradient? Okay. So direct preference optimization and proximal policy optimizations are techniques used to align LLMs with human references, with DP offering a faster, simpler, and more stable reward-free approach. What is reward-free approach? What is reward-free approach? A reward-free approach in a reinforcement learning is a paradigm where an agent explores an unknown environment and learns to navigate it without access to a reward function. Instead of optimizing for a single predefined reward, the agent focuses on learning the transition dynamics, identifying significant states, and collecting diverse trajectories to build an accurate model of the environment. So, what is the other option here? Yeah, these are other options like reward aware. In the tabular setting, reward free RL is typically more difficult than standard reward aware RL, where the simple complexities are differing by a factor of state space size. However, the linear MDPs they have shown to have similar. So it's reward free, reward agnostic, reward shaping, reward something like that. Reward free seeks to handle any reward, while reward agnostic focuses on a small class of rewards. Okay. DPO is direct preference optimization, offers a faster, simpler, and more stable reward free approach, while PPO offers a superior a bit more complex performance in dynamic high stakes tasks. DPO directly optimizes on preference data, reducing computational cost, whereas PPO requires training a separate reward model. DPO directly optimizes on preference data. Okay, DPO is direct optimization on preference data, and proximal policy optimization is training a reward model and then asking using it to train the LLM. Key difference between DPO and PPO: DPO treats alignment as a classification problem, optimizing the model directly on human preference pairs. PPO is a reinforcement learning algorithm that first trains a reward model to score responses, then uses that model to guide policy updates. DPO is generally simpler to implement and more stable to train as it avoids the complex reward modeling and RL stability issues associated with PPOs. Computational efficiency: DPO is faster and require less compute because it doesn't require running a reference model or reward model during training. Performance: while DPO is often faster, some studies show that PPO can still achieve better performances, particularly in complex and nuanced tasks. DPO is just direct preference optimization. You have some human preferences like ordered from 1 to n, and what you do is if you take model responses, if their model gave n responses, you rank them, and that ranking output is back propagated to the model directly, and model learns to follow those ranking going ahead. And in proximal policy optimization, you can be more nuanced or more smart about the feedback or back propagation thing, where a reward model can actually score different outputs, and maybe it can tell what it likes, what it doesn't, or something like that. Yeah, it's interesting. And a reward free wherein isn't oh, it's okay. It's saying that DPO is reward free, right? So a paradigm where an agent explores an unknown environment learns to navigate it without access to reward function. There's no reward function, it's just categorization. Instead of optimizing for a single predefined reward, the agent focuses on learning the transition dynamics, identify significant states and collective diverse trajectories to build an accurate model of the environment. Okay, well, let's just start.
Yes.
It was awesome. Actually, this guy is very good. Like, what channel is this? This guy is too good. What is Ensure Robotics? Sure. And if this guy has like 145, oh, 5K subscriber, I'm not sure who should have. Like, it's these presentation, they are so good. I think I'm gonna watch many of these videos going forward. So he says that modern ecosystems are changing faster than humans can observe. Field researchers rely on slow manual measurements, while satellites offer delayed, low resolution snapshots. There is a massive sensitive gap between the ground and the sky. My mission build autonomous intelligence system that fill this gap. Drones, sensors, and AGI platform capable of real-time environment understanding. I designed the entire stack myself. C-based transformers, HPC training pipelines, embedded flight controllers, sensors, ecological applications. Every prototype I publish, BLDC controllers, CPU optimized LLMs, IMU calibration rings, test benches is a building block towards the world's most accessible ecological intelligence system. If you're interested in embedded AI on CPUs, drones, flight dynamics, and attitude control, real world conversational through robotics, deep channel builds from first principles, deep technical builds from first principles channels for you. And this guy is from Canada. Yeah, I can go to it. Yeah, I think he has a lot more knowledge understanding. Maybe we can create a vision uh, or multimodal receptive where we can just point a camera and model will tell what is it thinking all the time, what is it seeing, and everything based on these data sets. That would be cool. And I think VLA, where like vision, language, and action would be on top of it. Like if model is thinking, then model can create some actions, and then those actions can be performed via hardware. But right now we can just have a vision language model. That would be cool. But I think like the modern LLMs, like let's say Claude Code, right? I think it uses all of these instruction, task specific, conversational, code generation, and multimodal. Because I think you can give it images or audios, videos, something like that, for it to analyze, and it can definitely generate code, and it is conversational. Like if you ask it, if you try initiating a discussion, then it can ask you questions, and it can carry on those conversations well, and it can task specific as well. Like if you just ask it, give me SQL, it will give you that SQL directly. So basically, they have all this kind of data, and they are doing good SFTs now. is GRP is different. So RLHF is mostly what is when you create a reward model, and DPO is direct preference optimization, and this is proximal policy optimization. GRP is group relative policy optimization, where key innovation is group based preference learning, relative ranking within groups. So you group based preference learning and relative ranking also is there within groups, more robust to preference noise process. So some may prefer more clarity, some may prefer simple response, some may prefer uh, detailed response. And even in the detailed response, you have ranking within the group process, generate multiple responses per prompt, rank responses within group, optimize relative to group baseline, self-play style improvement, benefits, better sample efficiency, reduce groups. Yeah. So now we are coming into pre-training. So fine-tuning these models. If you have some model and how you can fine-tune that model, how you can change those weights. And the interesting thing would be, is he talking about the fine-tuning in context of, like, let's say, RL or RLH? So is it in context of supervised fine-tuning or reinforcement learning, or is it in context of pre-training? Means, can I use parameter efficient fine tuning for you for fine tuning on certain SFT tasks or certain reinforcement learning tasks? It's my issue. I have to go for water. Yeah, we'll take water break. Oh, still water. It's 1 hour since I started learning LLMs. I guess we'll go for 1 or 2 more hours and then we'll call it that day. Let's start. So what we can do is when we will start our supervised fine tuning or RLHF or whatever DPO or even RLAIF or GRPO, whatever, we can use PEFT and we can use LoRa or something like some other technique, and we can just train that tiny fraction of parameters, which will reduce the hardware requirement for both element stages. What is LoRa? So he is saying that original weights are frozen, then small adapter matrices added, low rank decompositions, typical rank. So okay, so let's learn more about LoRa, QLoRa, and okay, we need Gemini. Can you teach me LoRa, QLoRa with clear examples, architecture, diagrams, top. So LoRa works on mathematical trick called low rank decomposition. Instead of updating the massive weight matrices of a model, it adds two much smaller matrices on the side. The architecture, imagine a model weight matrix is W size 1000 into 1000. Traditional way you update all parameters in W. LoRa way you freeze W and add tiny matrices 1000 into R and B R into 1000. The rank R is usually very small, like 8 or 16. Clear example. You want to teach general purpose model like Llama 3 to speak specifically like a medical doctor. Stay frozen model stays frozen. It doesn't forget how to speak English. LoRa adapter learns the specific medical terminology and bedside manner. You only save the small adapter file instead of whole new 15 GB model. QLoRa, quantized LoRa. LoRa on a budget. It takes the memory efficiency of LoRa and pushes it to further using quantization. How it is different from LoRa? It's 4-bit normal float NF4. It squashes the massive base model from 16-bit down to 4-bit. This reduces model memory uses by nearly 4x. Okay, 16-bit down to 4-bit, double quantization. It even quantizes the constants used for quantization, saving even more bits. Paged optimization. If your GPU runs out of memory, it temporarily offloads data to your system RAMs to prevent a crash. Clear example: if you have a mid-range gaming laptop with 8 GB of VRAM, impossible. Fine-tuning impossible. You would need 80 GB plus. LoRa might barely fit a 7 billion model, but it's risky. QLoRa comparably fits a 7 billion model with room to spare for training data. So base model state is frozen 16-bit, QLoRa is frozen 4-bit, small adapter matrices, memory needs are very low and ultra low. Speed it's very fast, slightly slower than LoRa due to dequantization. The rank are higher means the adapter can learn more complex things, but it uses more memory sweet spots. This is a scaling factor. A common rule of thumb is to set alpha equal to 2 into R. What is alpha? I thought you were mimicking the weights of 1000 into 1000 using LoRa, using low rank decomposition. Now you are saying we apply it on query and value. We can look at the image as well now. So it says original weights are frozen, small adapter matrices added low rank decompositions, typical rank. So by typical rank, it's 4 into 64 means 1000 into R. R is rank. Benefits for original parameters, base model preserved, multiple parameters, adapters possible, fast training and switching. First, you do 4-bit quantization, then you add adapters. Your adapters are 16-bit. You're absolutely right to catch the distinction. Let's bridge two concepts because they are actually the same thing, just as different scales of the model's anatomy. The big picture versus the specifics. When we talk about a 1000 by 1000 matrix, we are describing the single layer with the model. A large language model like Llama or GPT is essentially a giant stack of these layers. The transformer block one floor of the sky. So When we talk about a 1000 by 1000 matrix, we are describing a single layer within the model. A large language model is essentially a giant stack of these layers. The model is a skyscraper, while a transformer block is just one floor of that skyscraper, and the query value is specific rooms on that floor where the actual math happens. Why target specific layers? An LLM has many types of weight matrices: attention layers, feed-forward layers, embedded layers, embedding layers. Okay, so I didn't learn much about NLP or large language models before, even attention or transformers. So I don't know much about them, but I think we'll figure it out slowly and eventually. So an LLM has many types of weight matrices: attention layers, feed-forward layers, embedding layers. Okay. LoRa's goal efficiency. This strategy research, specifically the original LoRa paper, found that self-attention layers, specifically the query and value projections, contain the most adaptable knowledge for fine-tuning. If you applied LoRa to every single matrix in the model, your adaptive file would get much larger and training would slow down. By targeting just Q pros and V pros, you get 90% of the performance and 10% of the cost. How much math connects? Let's look at one specific room, the query project matrix, query projection matrix. The original matrix WQ, this is frozen 4-bit or 16-bit matrix of size D into D in Llama. The LoRa matrices, we attach these specifically to WQ. Summary: when I say target the query and value layers, I mean we are applying the that B into a decomposition specific to those specific matrices inside the transformer blocks rather than applying it to every single matrix in the entire model architecture. I don't understand Q pros, V pros, or different weight matrices like attention, feed forward, embedding, etc. Neither I understood that if each floor of the building has same materials applied but in different but just different sizes, or we apply LoRa on all the floors on same material or room, or just some floors. Every single floor in LLM building has two main sections. Every single floor in an LLM building has two main sections: the meeting room, the attention layer. This is where the model decides which words in a sentence relate to each other. Which words in a sentence relate to each other. There are three key projectors. like a search bar. It asks what I'm looking for. Like a label, it says that this is what I contain. Query key value. Once the meeting room figures out which words are important, it sends that info here to be processed and turned into a final thought. So there is a attention layer, there is a feed forward layer, and there is an embedding layer. Where do we put the post-it notes, Laura? When you target Q pros and V pros, you are deciding which rooms on which floors get the LoRa treatment. Yes, usually if you target Q pros, you apply a LoRa adapter to the Q pros room on every single floor of the building. All 32 layers of the Llama model. Do you apply it to every room? Not necessary. Standard LoRa, you only put adapters in the Q pros and V pros rooms on every floor. You leave the key room in the feed forward office completely alone frozen. Full target LoRa. You put adapters in every room on every floor. This is more powerful but uses more memory. Why Q pros and V pros specifically? Researchers found that these two rooms are the smartest parts of the floor. Q pros controls intent. What is the model looking for? V pros info it passes along. So key is this is what I contain. Imagine the model sees the sentence. The man went to the bank to deposit his money. Now imagine it sees this one. The man sat on the muddy bank of the river. The word bank is exactly the same, but the meaning is totally different. The attention mechanism looks at the surrounding words to the color in the meaning of the bank. In sentence 1, it highlights money and deposit. In sentence 2, it highlights river and muddy. Three parts query key and value. To do this highlighting, the model uses a system similar to a YouTube search. What I'm looking for, the word bank, asking, bank am I? What do I contain? Other words saying I'm river, I'm nature related word. What information do I provide? If you match with me, here is the nature meaning to add your definition. The process, the query looks like query bank looks at all keys, other words, calculates a score, how well they match. So is it like key? I think it's more like key. First, E1, E2, E3, En, embedding layers. Then we have key one. Key is the key is some A cross B matrices. Then we have query key. Key here maybe the man. Logic captures the core idea of weighting, but there are a few mathematical nuances that separate your representation from how the transformer actually works. Is value a combination of key and query? No, mathematically they are separate projections of the same input. Key and the query are used to calculate the attention score, the weight. Key and query are used to calculate the attention score, the weight. The value is the actual content that gets weighted by that score. If you are searching for a video on YouTube, the title tags are the keys. The actual video content you watch is the value. Correcting your mathematical representation. Your version was flawed, but there is a precise step by step breakdown using your example. The man went to bank. Each word is turned into the vector embeddings projection. Each embedding is multiplied by three different learned weight matrices. So query, key, and value scoring. To find the context for the word bank, we take its query Q6 and do a dot product with the key for every other word. Yeah, okay. We take query, what I said was we will take query and we'll take dot product. of keys of the other word. We turn those scores into percentage with sum to 1. Let's say the man gets a weightage and deposit gets 0.5. Weighted sum. This is where your formula differs. We multiply the weights by the value vectors. Okay, does this require a fixed input size? No, and this is the magic of attention. In older models like standard neural networks, you had to have a fixed number of input slots. Transformer handle variable sequence length because parallel comparison. The attention mechanism compares every word to every other word regardless of how many there are. Where you have 5 words or 500, the softness function always forces the weights to sum to 1. The math is just if your input is longer, the metrics just get bigger, but the process remains exactly the same size. Okay, uh, I I think I never understood transformer better than this. Yeah, I think so. Transformer has three weight layers. First embedding, then query key value matrices, then we go forward. What is feed forward? And we keep layering and so I'm saying embedding is embedding only provided by foundation. You have the structure almost perfect. Let's clear up those last two pieces: feed forward and lobby embedding versus the floors. What is feed forward? If the attention room is where words talk to each other to gather context, the feed forward room is where each word thinks about what it just learned. I'm the word bank, and after looking at money, I realize I'm a financial building. Feed forward. Okay, now that I know I'm a financial building, I'm going to update my internal data to reflect finance, vaults, security. The math, it's usually two linear layers with a non-linear activation like ReLU or CLU in the middle. It processes each word individually and in isolation. It doesn't look at other words, it just refines the information it already has. It is usually just two linear layers. So two linear layers are there with non-linear activation. It processes each word individually. So we did query, we took the query of that word, and we took the keys of the other word, and we did the dot product. We found the softmax, and using the softmax, we took the value layer of all those words, and we got some representation of a weight. Uh, uh, yeah, we got some weighted values, and then we take this weighted value for each word, and then we that weighted value is then there are two feed forward layers, just a bunch of weights which are learned to make things complex or to have better understanding, and then there's a relu on top of it, and it's refined the information it already has. The foundation versus the floor. The lobby embedding converts two word IDs into a list of vectors. The floor layers, they don't re-embed the word, instead they transform that vector. How it moves through the building. Lobby, you enter a generic bank vector. The attention room sees money nearby. The vector is modified. It's a floor one slightly changed. It says money. It's a bank, but I'm related to money, so I may be a money bank or maybe SPI or something like that. The floor takes the output of the floor one as its input. It's even more nuanced. The sentence is past tense. By the time the vector reaches its root, it's no longer just a generic bank vector. It's highly complex mathematical representation of a financial bag in a past tense sentence about a man depositing money. The input for every floor after the first is simply the output of the floor below it. The full building blueprint. The man went to the bank. The lobby is it's just embedding layer turns it into row numbers. Then there are queue, query, and value matrices which are for context gathering. We add and norm a hallway that's clean up the math. So there's a feed add and norm. What is add and norm? Okay, I didn't understood what is add and norm. What is the need of add and norm if we have what is the need of for these and what are they if we already have feed forward room. No, skyscraper analogy. Add and norm are like elevators and the cleaning crew. Without them, the building would collapse before you reach the fifth floor. They are elevating and cleaning crew. Okay. Even if the attention room and the feed forward rooms are perfect, the math inside a 32-layer building has two major problems that add and norm solve. Residual connection. Okay. The problem is words information travels up through the 32 floors of the intense math. The original meaning can get lost in translation. By the floor 20, the model might forget that the subject was man. Okay. Instead of just sending the transform data to the next room, we add the original input back to the output. Okay. Instead of just sending the transform data to the next room, we add the original input back to the output. It's like a skipped link or an elevator. It allows the original signal to flow directly to the top of the building without getting distorted by the rooms along the way. Okay, it's saying it was a bank. Don't forget that. Add it, do a normalization or whatever. The problem neural networks hate extreme numbers. If one layer outputs a huge number like 1 million and the next layer outputs a tiny one, the math becomes unstable and model explodes or dies during training. The solution layer normalization. Before data leaves the floor, the cleaning crew comes in and reshapes the number so they are all on the similar scale. Imagine a group of people shouting at different volumes. Layer norm is like a sound engineer who adjusts the microphone so everyone is here at the same comfortable time. On every floor, you actually see the pattern twice. Input, attention room, add and norm, result, feed forward, add and norm, next floor. When you look at the Q LoRa infographic from your first message, LoRa only touches the rooms, like the weight matrices, query value, or something or sometimes the feed forward. LoRa doesn't touch the add and norm layers. Why? Because the add and norm layers are the structural stability of the model. They don't hold the knowledge of how to speak like a doctor. They just keep the math healthy. By leaving them frozen, we ensure the model stays stable while we use LoRa to teach it new tricks in the attention and feed forward rooms. Okay, so what do we add in after attention and after feed forward layer? After attention, we have weighted value of surrounding or opinion of surrounding about the bank, and after feed forward, it has more refined taste, like bank, which stores the money for humans, etc. So what do we add in these? The original embedding of bank. How can something go wrong here at this stage? We're learning so much. What the fuck, yeah. And do we pass the embedding So I think by using this analogy, right, we are learning so much better. So it's saying it's a fantastic question. This is the part that makes skyscraper work. We add the input of that specific floor. It's not a connection back to the lobby, it's a connection between adjacent floors. What exactly are we adding? On floor 10, we don't go all the way back to the foundation. We take the information exactly as it looked when it entered floor 10. The cycle on the floor 10, the input vector representing bank already processed by floor 1 to 9. The attention room calculates context. The add step, we take the input and add it to the attention output. Input is the input we got in the floor 9. We have new context, but we have not lost the pre-context identity the word had when it arrived at this floor. The feed-forward rooms refines the test as you output it. The add step, we take the result from step 3, this thing, and add it to feed-forward output. Why we don't why don't we add the original foundation embedding? If we always add the raw foundational embedding to every flow, the model would struggle to evolve. The goal is gradual refinement. Floor 1 adds little context, floor 2 adds little more to what floor 1 already did. Floor 32 has a massive mountain of 32 layers of context, all stacked on top of each other. The identity problem, why we add it all? If you just pass the message by the 32-second person, it's grabbled. The ad is like the 10% saying, here's my improved version of the message, but also here's exactly what 9% told me, just in case I messed it up. This ensures that even the attention room, the floor 10, goes crazy and outputs total nonsense. The add step preserves the scene data for floor 9, allowing the model to stay on track. How this looks for Laura? When we use LoRa, we are only tweaking the improved version part of the message. We are only tweaking the improved version part of the message. The original bit generates its part. The LoRa adapter adds expert's opinion. Then we that whole combined result is added to the input from the floor below. I didn't understand this part. It's a chain of addition. Each floor builds. I did not understood the fourth point, how this looks for Laura. Also, I would love to understand how it's interesting. To understand point 4, we have to look at what happens inside one of those rooms, like the query room where Laura is installed. Okay, now we have full understanding of the transformer. Okay, if this is the transformer, it is, then we have full understanding. Normally, a room has one big, heavy frozen block. The original model waits. When data comes in, it hits the block and comes out changed. With LoRa, we add a side entrance, the adapter. The input enters the room, it splits. Path A, it goes through the frozen block. This is the old knowledge. Path B, it goes through LoRa matrices A and B. This is the new training. At the exit of the room, path A and path B are added together. The key, because we add them, the model keeps its original intelligence but shift its origins opinion based on the LoRa matrices learned. It's just like a manor, an assistant given an answer together. The rank is the width of the side entrance. It determines the capacity of the new information. Imagine the original matrix is massive. LoRa breaks this down into two screening matrices. Site entrance is now a wide valley. The model can learn complex new tests or specialized knowledge, how to diagnose, how R determines the info. Think of R as a resolution of a photo. Like a pixelated images, you can get general shape of the new knowledge, but none of the fine details. This is usually enough for changing of the style of the talking. Like a 4K image, you can capture deep, complex facts. However, if R is too high, you lose the benefit of the LoRa because the adapter becomes too heavy and slow. What I don't understand is we add the results after uh, let's say ninth floor got some input and it gave final output which will go as input to 10th floor in normal base model. Now when we add LoRa, we are adding LoRa on the complete floor, not just attention rooms. And we take ninth floor input, process it using LoRa, and add it to ninth floor base output. Also, don't we need normalization after add? You ask if LoRa is added to the complete floor. Technically, no, we don't wrap the whole floor in one big LoRa. Instead, we go inside the rooms, attention feed forward and attention LoRa, and attach LoRa specifically to the wet matrices, the W block inside them. Okay, the floor on the 10th floor, the floor on the 10th floor. Input from 9th floor arrives. It enters the attention room. Inside the room, it hits the query matrix WQ. The math result input into WQ plus input into A into B. Note the LoRa part is added right there inside the room before the data even leaves the attention layer. Then once the attention room is done, the combined result goes to add and now hallway. The double addition. This is tricky part. There are actually two different additions happening. The LoRa add happens inside the room. We add the LoRa opinion to the base model. Attention, the residue that happens in the hallway. We take the output of the room and add it to the original input of the ninth floor. Do we need normalization after LoRa? Yes, and this is here is the magic because if we inject LoRa inside the existing layers, the data naturally flows into the original add and norm hallway that already that was already there. So we uh, apply LoRa on weight query weights and value weights, right? And you said We rely on whole weight to normalize. But since query weight, since query now has both normal frozen and LoRa into it, and then it goes for dot product with key, won't it produce some messy output if LoRa layers added something freaky? If the LoRa path outputs huge numbers while the frozen path outputs small ones, the query vector becomes a mess and the dot product with the key will produce wild attention scores. To prevent this messy output, LoRa uses a secret weapon called the scaling alpha by R, the volume controlled scaling. When we add the LoRa path to the frozen path, we don't just add them one on one, we use a scaling factor to make sure the LoRa opinion doesn't drown out the base knowledge, the math. As we discussed, this is the width of the LoRa pipe. This is the constant, usually 16 or 32. The magic by dividing alpha by R, the model automatically strings the LoRa values. This ensures that even if you change the rank, the volume of the LoRa contribution stays stable. In with scaling, what if LoRa is freaky? If LoRa Yes, let's jump to QLoRa. So, how much time is it? It's 1 hour and 40 minutes, and we're learning everything that is to learn about LLMs. First, we learned about attention layers, feed forward layer, then embedding layers, normalization, layer normalization, addition, softmax is where is softmax, where is LoRa, and yeah, and it's 2 or not like 37 minutes or something. Yeah, and we understood, I think, most of it. We understood the whole transformer architecture. Hmm. Now, even we understood like not just the transformer architecture, but we understood the pre-training part. Then we do pre-training through transformer. where there's a cross entropy loss. Next token prediction thing is there. Then we through LoRa or QLoRa we can do supervised fine tuning or RLHF or RLAIF or whatever you want to call it, the reinforcement learning variant of the large language models. And when we do that, we use another kind of cross entropy loss, uh, which can which works on just the complete sentences or complete sequence instead of just the next token. And there you got the best LLMs that you need. And yeah, for reinforcement learning, so yeah, I think we understood most of it. Now let's go back and understand QLoRa, and let's finish this video as well. How much long is it? It's 15 minutes. I think it will take us 30 minutes more, and it's already 150. So by 2:30, let's try to finish all this. To understand QLoRa, imagine you are trying to fit the 10-story building into a tiny suitcase, your GPU. To understand LoRa, the frozen building is made of heavy 16-bit stones. QLoRa turns that stone into lightweight 4-bit plastic but keeps the post-it notes LoRa adapters in high-quality 16-bit paper. This is the magic trio that makes QLoRa work. 4-bit normal float, the beta squish. Normally, when you compress numbers, quantization, you lose a lot of details. Standard quantization, like rounding to 3.0, you lose the 0.14. Normal float and a 4. This is the specialized math format that knows LLM weights usually follow a bell curve. Most numbers are near zero. It maps the 4-bit values more intelligently, so you lose almost zero accuracy while using 4x less VRAM. Okay, what is normal float? So normally when you compress numbers, quantization, you lose a lot of details. Standard quantization like rounding, you you lose the 0.14. The normal float and a 4. This is the specialized math format that knows LLM weights usually know follows a bell curve. Most numbers are near zero. It maps the 4-bit values more intelligently, so you lose almost zero accuracy while using a 4x v less VRAM. It's interesting. This enough for normal fraud 4. We have introduced some new quantization way based on the bell curve or something like that. Crazy. Double quantization. Every compressed layer needs a small scaling factor to tell the model how to decompress it. In QLoRa, we even quantize the scaling constants themselves. It's like saving space by folding your clothes and then vacuum sealing the bag they are in. It's an extra zero point 0.5 bits per parameter, which adds up to gigabyte on large models. Paged optimizers, the safety wall. This is the guardian angel for your GPU. The problem during training, if your data is too long, the GPU runs out of memory and crashes. The solution QLoRa uses paged optimizers via NVIDIA's unified memory. If the GPU fills up, it automatically spills the extra data to your system RAM temporarily. The training slows down slightly, but it never crashes. Okay, it's just memory optimizations. QLoRa workflow: load the big model in 4-bit. Whenever enters a room, the model temporarily upscales that specific 4-bit chunk to 16-bit just to do the math. When a word enters a room, the model temporarily upscales that specific 4-bit chunk to 16-bit just to do the math, calculate, do the LoRa math in high quality 16-bit, discard, throw away the 16-bit upscale version of the base weight and keep the 4-bit one. Let's don't dive more into QLoRa now. We'll just focus on this part.
Base model and lose general knowledge. So only needed for major domain shifts, which is rare in practice. So let's look at, the practical example. So here's a practical implementation. You load the base model, frozen, and LoRa adapters with rank 16. So here you can take, this is your base model, and then you create your LoRa.
You defined R, you didn't define the alpha, your target modules IQ and V and LoRa config, then you get PFT model. Uh, PFT is like parameter efficient fine tuning model, and you gave the model, you gave the LoRa config, you got the PFT model, your results 1 million parameter frozen plus 14 million parameters trainable. Training cost very Yeah, I'm just here to post a thank you, and then we'll go to the Gemini chat and we'll discuss. Because I think, yeah, let's go and let's continue this chat for another 10-15 minutes or something. The transform is simply the architectural style of the building. Think of it like if neural networks are the buildings, if neural networks are the building, then transform are a specific modern design that uses floor, layers, and rooms we just discussed. Think of it as neural networks are the building. Neural network is the complete building. Then transformers are just specific modern designs that uses floors and rooms, we just discussed. When people say a model is encoder only, encoder, decoder, they are talking about the shape and the purpose of the building. Encoder only, the reader, the goal to understand and categorize text, to understand and categorize text, to understand and categorize text encoder. The architecture, every word can attend to every other word in the sentence at the same time. Example, but if a researcher reading a full page of notes to summarize them, they have all the info at once. Decoder only, the writer, to predict next word in the sequence. To predict next word in in a sequence. This is what GPT, Llama, and Mistral are. The key difference: a word can only attend to the words that came before it. It cannot see the future. Oh, so it just encoder only to predict the next word in the sequence. Encoder, decoder, the translator. to take one sequence and turn it totally different one. It is actually two building connected by a bridge. The encoder reads the input English and decoder writes the output French. Since LoRa and QLoRa are used mostly for generative AI like ChatGPT, we almost always apply them to decoder only. In decoder only model, the attention room is a mask. This mask ensures the query from the word banks can only. So can the same architecture can the same transformer architecture if you see even encoder only architecture is about predicting the next token for the summary and decoder only is prediction of next token from future. They are not much different. If you looked at the code for encoder flow and decoder flow side by side, they would look 99% the same. However, so what we should ask is, let's go to ChatGPT and let's ask it, does encoder only transformer architecture and decoder only architecture model would look the same. But they're not exactly the same. Both use transformer block structure, but the attention mechanism and flow differ. Let's break it down slowly. Okay, it's generating some images. The mechanical difference, the mask. This is only physical change in the attention node. In an encoder, the windows are clear. Encoder, the windows are clear. Every word can see every other word. Bank can look at money to its right and man to its left simultaneously. In a decoder, the windows to the right are painted black. It's called causal masking. Bank can look at the man, but it is physically blocked from seeing money. Why? Because if decoder could see the next word, it would cheat during the training by reading the answer instead of learning to predict it. The mask. In an encoder, the windows are clear. Every word can see every other word. The bank can see the money and the man. In the decoder, the windows are right on right are painted black, which is called causal masking. Bank can look at man, the past, but it's physically blocked from seeing money. The loss function, the exam, we are 100% correct. The way we grade building determines what it becomes. Decoder only next token prediction. The goal predict word n plus I, n plus 1. The loss cross entropy loss, we check if the model's predicted probability for the actual word was high. The arcade set on the models is met, it was met, loss is low. Encoder only mass language modeling. Goal fill in the blanks. The loss also cross entropy, but we hide a word in the middle. The encoder doesn't usually use for summarizing by generating text. They are used to turn a sentence into a single meaning vector embedding that a classifier can then use. Can one building do both? Absolutely. In fact, many researchers now use prefix LM architecture where part of the sequence is unmasked and rest is masked. How this affects slowdown? The architecture stack of mask nodes. The loss function is always predict the next token. The lower allows to shift the values of each next token to match the specific summary. Okay. Mask and loss they differ. And what does the chat GPT telling us? So these are input embeddings. These are positional encodings that we have. We have multi-head attention, and we add and do normalization. We had feed forward, add and norm. Then it goes here. This is the add and normalization. Layer normalization is there. This is the input. Then it again goes to multi-head attention, add and norm, feed forward, norm, linear, softmax, output priorities. Positional encoding, output encoding. These are in layers. Okay, now you know the next token. So these are output embeddings, shifted right, again to positional encoding, mass multi-head. What is mass multi-head? They're saying this is the encoder only transformer, and this is decoder only. Mass multi-head attention, layer normalization, feed forward, layer normalization, and layers like this output. Input embedding vectors. Oh, it's really interesting, but it's already 2:18. We'll continue this stream tomorrow. Yeah, we'll continue this stream tomorrow. Bye.